So everyone, welcome to our IEOR online seminar series. Today it's our great pleasure to have Professor Jianqing Fan visiting us and giving us this online talk. Actually, Professor Jianqing Fan really doesn't need any introduction, but I will just do a brief one. So at Princeton, Professor Fan is a professor of finance, professor of statistics, and also a professor and has been a department chair in the Department of Operations Research and Financial Engineering. And Professor Fan is a statistician, financial econometrician, and a data scientist. And actually, Professor Fan has done highly cited articles and books in all these areas. Professor Fan also has received numerous awards, including the COPS President's Award, the Morningside Gold Medal for Applied Mathematics, the Guggenheim Fellow, Paul Xu Prize, and a Guy Medal in silver. And Professor Fan is also an alumni of Berkeley, and he received his PhD here in 1989. So without further ado, we'll welcome Professor Fan to give us the talk on deep Q learning.
All right, Zhe, thank you very much for your kind introduction. Coming back to Berkeley is always my dream. I meant to be there I think in the early June, but unfortunately due to close up, I couldn't be there. So hopefully I'll have another chance to see you in person. So I always been your neighbor when I was a student. I stopped by the department also quite frequently there. And now I'm in operation research department myself. So I'm particularly pleased to have an opportunity to talk to the ORI group. So again, thank you for the invitation. So when I was invited, the first thing I say is, well, what should I talk? This is always the problem, right? So what to talk to, a group basically know everything. So I thought maybe it's good to talk about, from data to decisions. So therefore I just pick up a topic on deep Q learning, which I hope that will suit the operation research department well. So this is based on joint work. Oh, by the way, for those people who haven't been here, this is Princeton's office departments. Very transparent because it's financial engineering in mind, so it's very transparent. Okay, so here is the outline of my talk. So first, I'll give a brief introduction to set up notation and the problem, and then I'll add a little bit background on Q learnings. Then in order to learn the value function, I need to introduce offline deep statistical regression, and then finally I'll talk about the properties of deep Q learning. And finally, if time permits, I hope I'll talk about two-agent zero-sum game as an extension. So this is based on work with Zhorang Yang, who is currently my PhD student, done a lot, way more work than the collaboration we have here on reinforcement learning in a matter of last 2 years. And Yuchen Xie is a student in Northwestern of Zhorang Yang, who was a former student at Princeton too. So here is a brief introduction talking about the AI. So lots of people, typical success of AI, typically people thinking is applications in games such as Atari or Go or spacecraft or text hold'ems and so on, or controls like robotic hands, free managements, and automatic drivings. Or interact like recommendation system, personalized medicine, ride sharing, and so on. Right? Explore like navigation and so on. So it's no doubt that what has changed. The reinforcement learning has been a very old topic, and so there's deep learning. Right? So what has changed? I think what the contribution to the success of artificial intelligence due to representation power of deep neural nets. as well as decision making by reinforcement learning, mapping from function learning into decision. And then, of course, thanks to big data and modern computing power, making many of our dreams possible. But there's also many challenges in artificial intelligence, right? So, for example, in AlphaGo training, to play like 29 millions of self-play games, it will take about 40 days of training in supercomputer. And for Alpha Star of like 200 years of real StarCraft play will take 44 days of training, and Rubik Cube of 10 years, 10,000 years of simulation will take 10 days of training. So no wonder in the blog, right, the people may say, hey, deep learning still doesn't work yet, and so on. So there's still a lot of like algorithm as well as challenges that we really need to solve, right? So the challenges to single agent reinforcement learning include like nonlinear function approximation, non-convex optimization of policy data and exploration, right? So computational challenge at least include convergence of algorithms and also global optimality issues. And statistical challenge at least include efficiency of policy learning as well as active sampling. So there's a lot of great success, empirical success, but there are still limited theoretical understanding, though recently there's a lot of paper in understanding different aspects of reinforcement learning. And in addition, like when we consider like a multi-agent reinforcement learning, there's non-stationary environment, partial observation, scalability, and so on and so forth. So in this particular case, there are limited empirical success, even limited theoretical understanding. So even for two-player zero stochastic sums, we have very limited theory available for us. So the talk of today is really just to provide theoretical understanding of sampling efficiency of deep Q learning in reinforcement learning, as well as zero-sum stochastic games. So there are two books here, right? So one is deep learning, everybody knows, and the other one is reinforcement learning, and we probably want to bridge the gap. In the middle, my student put a book that I wrote with my co-author in the last 10 years, finally just finished in the August. It's on Statistical Foundation of Data Science, which any learning algorithm here can be applied to deep reinforcement learning. So now let me begin with some backgrounds to set up notations. So this is really on the Markov processes for and Q learning. So the Markov decision process is work as follows, right? So when given a state, right? So agent see the state and have to take an action according to a policy or a certain distribution. This could be deterministic, could be random, right? And then once you make a decision, the environment give you rewards, right? As well as change the state to the next state. And then you see the next state again, you make a decision and so on, right? So this is really the game or the Markov decision processes that we are doing here. So in this case, I will later on denote S as a state space and A as action space. And then the one that govern the play or the rule of the play is the policy, right? So given state, I take an action. So this would be the action is taken from given the state, I take an action. And once you take an action, you receive, the state changes, right? So you, given the state and action, the environment changed to st+1, a new state. And also you observe a reward, which is typically unknown. And you can also regard this as a bivariate process, right? So f of st+1 and rt+1 in general. So whenever you see the state, you take an action, you got a reward, and you move to the next state. So these two could be regarded as as a joint reward function. So this is the Markov decision process. And the example we all know, like, could be play games, right? So in the Super Mario Bros. This brother, so this would be the state would be the current image that you see. The action you could really take a left or a right or jump or duck, right? And the reward you can get mushrooms, coin, flowers. I really do not know the game, and then the transition kernel specified what is the next frame of the image, and then pi really is the policy. Whenever you see an image, how you control it, right? So in this particular case, certainly people will easily imagine convolution network would be particularly useful to learn to do feature extraction based on the current games. So now, as a statistician, or naturally, we ask what to learn and what to act, right? So of course, what we want to learn is the transition kernel, for example, like given state and action. What is the next state, right? And the reward rule. So from the past data, right? Both of these learn from past data. And what to control, of course, is the policy. That's the only pi that you can choose. So in other words, the transition kernel and the reward function are from the nature or from the system. So you have no control, but what your control is policy. Right? So based on what you observe and how you improve the policy. Now the question is, so how can we achieve this? And so in order to do this, so we need there are many approaches, and one particular approach that we do here is really through action value function. So action value function is defined as follows, right? So given the current state and given the current action, current state and current action, right? So then you got the reward, RT, and you discount to present time. So there is a discounted infinite horizon Markov decision that we are talking in this particular problem. And so this is this is the the expected future rewards, right? So discount to present time, and given the current state and current action, and this taking under your your policy. And this one, of course, satisfies what's so-called the Bellman equation, which is really saying is what is pleasant reward, right? The current reward you get. And then now the state move to, given the current the state, now you got the current reward. Now it moved to the next state, right? So so state is now moved to S prime. And action you're taking is A prime, right? So it will be to the next one. So this is the Bellman equation is satisfied. And our goal is to find pi star that maximize the reward function. So once you, and then once you, you find the optimal policy, right? So the value action function, or sometimes called state action function, I denote this as a Q star. So this is really just the Markov decision problem, and how once you give a Q function, you really just taking what's so-called the greedy policy, and you get in the optimal solution. So so let me define, just introduce the notation of Bellman operator, optimality operator, which basically is defined as follows, right? The immediately, given the current state and action, is the immediately award, right? Plus the next step, right? So you're taking a greedy policy in the next, now state transition to the next step as prime, and you take the greedy policy of this Q function and then discount it. So in other words, is really just the upper bound of this Bellman equation, taking maximum with respect to this A, the optimal decision you take with respect to this A prime. Well, anyway, so this operator is very well known, is contraction, right? And of course, it's contraction. If you iteratively apply this, so then you'll find a fixed point, and this fixed point of convergence at linear rates. So in other words, Q star, if you knew the system, you knew the T, you knew the T, and if you knew the T, you just keep iteratively apply, iteratively apply the, the equation here, and then you got the, you got the optimal Q star, and then the policy, the optimal policy you use is just greedy policy. If you see the state here, you see what is the optimal action, in this case here. If you see the state is here, you find the optimal solution. The optimal is here. If you see the state here, it's like this. So, and so on. So once you find Q star, the solution is very simple. So the only trouble is that we do not know the T, right? We do not know the system. So we have to sample the data and learn this T, and therefore we could iteratively apply this policy. So an early work is by Walking and Dalen, so which really just apply this Stochastic approximation to solve this Stochastic approximation to solve the Bellman equation. So in this case, we is really asynchronous, right? So you update an entry every time. So for example, if your current state is 2 and is 4, and you take action 2, so you know next you want to update is 4.2 entry. And then the immediate reward is 1, right? So you get 1, and then 3 is the next state, right? So the next state is 3. The optimal in next state is 9, right? So among this column, so you got a 10, like this. So this is really the early work of Q-learning. And lately, there's a lot of, work on these issues. Too many even for me to. Too exhausted here, right? So this would be including policy improvement, policy optimization, including Q-learning. So these like for tabular cases, but there are many of my friends in Berkeley, like Martin Wainwright or Michael Jordan, write nice papers on this. And then also there's a function approximation approach, including in statistics that are called dynamic treatment regions and so on. So it's all included here, but it's way more literature than I were able to present here. So our question is direct to the point is, how do I estimate Q star? And so I estimate Q star. So how do I get to estimate the optimal policy? So in order to estimate, to get in an estimate of this Q star, I need to do function approximation of this. And this leads me to quickly introduce deep neural nets and is some recent results. So it's very well known that deep neural nets looks like this, right? So given pixels of image, you do linear combination. So you got the new next layer of neurons, right? So you do nonlinear gating, and now you do linear transformation, nonlinear gating, and so on, right? So this is deep neural nets, and this sigma is typically called activation function. W here is called weighted matrix, and B is called bias, but this is just a few names. So if I write deep neural nets in a little bit more mathematical form, right? So it's really a composite of linear combination of initial inputs, right? So then you do nonlinear gating, right? And now you do linear transformation of this, right? And do nonlinear gating. So it's just keep applying the composite of linear, transformation plus nonlinear gating and so on. Yeah, so I assume the dimensional inputs throughout what my talk will be R. And of course, for our specific case, output is 1, will be the Q value function. So this is really the neural nets. And so let me also define the sparse relu network. So for simplicity, because every time whenever I see W and B, so if I have to write twice, so I just use W tilde to include both matrix and the vector of the transform. So then I define the sparse relu neural nets with the width will be D1, sorry, D1, D2, and so on, right, to DL plus 1. So this is the width. S is control the sparsity, V control the total value, and L is the depth. So it's any function whose, I mean, the network weights plus and bias is upper bounded by 1. Right, the total non-zero elements is bounded by S, and then the function F is totally bounded by V. So this is the sparse neural nets that the notation I use. So neural net is particularly convenient for, for composite function, because neural net is a composite function to begin with, right? So let me define the GJ, the J's function vector is like from PJ dimension, is an ambient dimension. This could be quite high, to PJ plus 1 dimension. So this is the definition. So this PJ is ambient dimension I have. However, each component of these GJ is really low dimension. So let's say it has intrinsically is, let's say, TJ dimension. So TJ is the intrinsic dimension. It could be 1 dimension, could be 2 dimension. And then the associated smoothness, let me know by BJ. So this class of function I'm going to denote using this notation. AJ, BJ is just, and right, is the interval. Usually we'll assume 0 and 1, so it's much easier. And TJ is the dimension, the intrinsic dimension in any of this function of G. And then the function of class that we are considering is the composite of many multivariate, multi-output functions, G1, G2, and GPE. So, and this one I will denote using the notation like this to denote the composite function. I know notation is a little bit heavy and also a little bit confused, but if we see a function like this, right? So let's say, for example, a function like this is a 5-dimensional function. So it's a really composite of additive, this plus this components plus these components, right? So the intrinsic dimension, if you look at it, there's a 2-dimensional function here, right? So there's a 2-dimensional function here and 2-dimensional function here. So even though it's a 5-dimensional function, intrinsic dimensionality is only 2 dimensions, right? So this is TJ here is really trying to characterize the intrinsic dimensionality, right? So in this case, let's say maybe it could be here, it could be just 2 dimensions. Now, in order to approximate the function of this well, right? So we need to know how smooth the function up to here and how and so on. So I define, so what is the smoothness of this FJ, which is the composite of the last, starting from J's layer all the way to Q's layer. So this is the smoothness function. So it's certainly depending on how smooth each function this beta J is, right? And then of course also depending on the bottleneck here. So if some of these are not smooth, it will not be smooth either, right? So therefore it should be depending on how smooth this GJ function here is, each component, how the smoothness of GJ, then plus the bottleneck they have there, right? So this is the minimum of this, right? It cannot be more than 1. So this will be the smoothness of FJ starting from here and on, right? So this is the smoothness. Okay, so and then there's a very nice paper to be published, or maybe already published, in the Annals of Statistics as a discussion paper by Schmidt and Heber. So which basically is saying that for any function G in R dimension, right, and has smoothness beta, so they exist a relu network with the depth is L and the width is really equally width, and then sparsity S, such that the approximation error, so the G function in this holder class can be well approximated by by this sparse neural net with the error here is 2 minus m. So therefore the depth doesn't have to be very long, just the logarithm order is enough. And this is related to the smoothness is the width, right? So more precisely, this is the L is linearly depending on the m here, right? So and the depth is linearly dependent on n here, right? And then the sparsity is of course the multiplication of these two. So the total number of parameter there. So this basically shown that neural nets does have representation power, approximation power of holder class. And interestingly, they also represent the following statistical results. So if I let least squares estimator in my sparse neural nets given n samples, and if I set this, right, so this is really the GJ function, the J function, the difficult as non-parametric rates of estimating this Fj here, right? So if I estimate in this Fj, so this Fj has has smoothness beta J star and the intrinsic dimension Tj. So then the optimal rates from the non-parametric regression literature is really your smoothness divided by the intrinsic dimension, right? And of course, I take the worst case because I take the worst case if they have different degree of smoothness. And now I set AN to be this non-parametric rates. Schmidt and Heber basically showed that the mean square error is of this order times all these are just of log n order. So in other words, so this would be non-parametric, the rates of convergence you get, so long as the depth is of log n order, and then the width is big than something, and then this is the sparsity. So this is an abstract way of saying, but if I really say a single words about these results, it basically is saying that if I use neural nets, even though I do not know the degree of smoothness, you'll adapt to the optimal degree, optimal rates of convergence. Even though I do not know what is the intrinsic dimension beta j, tj for each composite function, I mean, this least square estimator doesn't depend on tj itself, will adapt to low dimensional structure. So this is really what this basically the result says. And I look at the proof and construction. It's pretty similar to like a wavelets construction of, wavelet multi-scale construction. And this also explains why you could adapt to unknown degree of heterogeneous degree of smoothness. And then adding addition is that it adapt to unknown low dimensional structure F2. So in the paper by Michael Kohler and Langer, so they show similar results, but actually you could either let the width fixed, and then you have deep neural nets, or you let the width fixed at the width, the depth at the log n order like here, but then the width you had to be a little bit bigger. And this is a little bit nicer network, require less sparsity. So anyway, so this is basically the results that I would like to introduce before we go to our technical results. So here basically, at least for me, is clearly demonstrate the adaptivity of neural network to unknown degree of smoothness, beta j here, and to unknown low dimensional structure, tj there. So now let's talk about deep Q learning. So the purpose of introducing a deep neural net is to approximate Q table by using deep neural nets, and I abstract as Q theta, and it depending on unknown state and the action. So the early work in this, right? So long as you using the same theta in your gradients update, So let me not get into detail of it. So Richard Stanton Sutton called this like a dead triangle because you're using the same theta. So this algorithm would not converge. So in the Nature paper by Mint and his collaborators, David Silver is one of those people there. So they basically use two traditional tricks, right? So one is what's so-called experience relay. That is, if you play game many times, you store your data, right? So this is the action, this is the state, this is the action. So this is the reward received, and this is the transition to the next state you got, right? So you store in this and then subsample. And when you train the neural nets, you use a separate neural nets to to approximate the target. So, in other words, so how do we really estimating the Bellman optimality operator T is as follows. So first, I sample, right? Let's say this 10 to the power 6. I may sample 10,000 of this SI and AI. Okay, with this SI and AI regarded as X variables. And then I have current neural net, let's say Q, a current approximation of Q. So I calculate this YI this way, right? So I calculate mimicking the Bellman operator. I calculate YI this way. And now I regress this YI on my XI, right? So if I do this regression YI on my XI, from a statistical point of view, you are really trying to learn is conditional expectation, which is the mean regression function. And the mean regression function, if I take expectation here, given as an A, is really just the Bellman operator, right? So the Bellman operator, optimal operator, because this S prime is coming from the transition, kernel. So therefore, I will run linear regression. Right? So this I will run neural network regression, and in practical implementation, of course, you use stochastic gradient updates. But from statistical point of view, let me say that you are able to optimize this Q hat, and then you will getting an updated network, and this network called deep DQN, and has been very successfully applied to many learning tasks. And in the paper, they compare many examples, and many of those actually working as good as experts level. So now, in order to understand this deep Q network, we modify slightly, and hopefully that will be a little bit easier to understand what our algorithm is, and so on, right? So recall the ideal situation. If I know everything, if I know the whole system, and the reward function, this is the Bellman optimal operator would do, right? Starting from any arbitrary value, you apply the Bellman operator, you get to here, you apply Bellman operator again, you get to here, right? And you keep doing this, then you get into the true Q star. Now, of course, I do not know what is the system, so I have to sample the data, and this is really what we are doing here. So let's say you give me a sampling distribution, mu and f, right? So you give me a sampling distribution, mu and f, and you tell me how many iterations you want. And every time you tell me how many data points you want to do of policy learning, right? And then you give me an initial artificial, let's say 0 to begin with. Right, so you keep doing, you iterate, right, doing this iteration. So first you sample state and action from this, from your scheme, let's say uniform, right, from your scheme. And then of course you observe the rewards and you observe the transition, right? So once you observe reward and once you transition, and given the previous Q, you could calculate what is the Y value. So in other words, so you pretend to apply Bellman operator to compute what is the Y value. Once I have Y value and I have X value here as an A here, right? So I just run regression. So this is the regression I'm running. And then I get an estimate of my regression. So I update my Q to Q star. So really, our algorithm is very much mimicking what would have been done if you are in this ideal situation, right? Starting from Q0, right? So you sample n data points. So you calculate your y. Now you run regression. Is the deep neural net. You run your regression. You get Q1, right? So in this case, you are really getting an estimated Bellman operator. Now you are in this Q1. So the next one I'm going to do is sampling again, right? Making n sample again. And then I could do this stage. So in other words, I learn based on new sample, I learn a new operator, and then I apply it, I get Q2 and so on. So this is really the real neural nets I'm working on. And in between all these is our target neural nets. So the Q star that here we are TQ star is our really target neural nets, which is right because of statistical estimation. You are never getting the true one, but you are getting true one with estimated errors. So this is the algorithm that we use. So in other words, we do off policy sampling, and then we do regression, and we do off policy sampling, we do regression. So we keep every time we learn a Q. Now the question is how to analyze this procedure. So this is part of my talk game. So how to analyze the neural net regression error, because this neural network error will propagate through the reinforcement learning algorithms. And in addition, the statistical error is also correlated with the covariance. So they're creating additional challenges. So let me first summarize the result we got first. So I assume the sample space or state space is in our dimension, and the action is finite. And then I assume that the data distribution I sample, right? So I use this to collect S and A. So this design distribution is regular, so it's explore all the states. And in the regression process, I use this sparse neural nets, right? And I assume that the Bellman operator applied to my Q network is still composite holder, and they can easily be shown with certain kind of smoothness. And at the end of the day, I evaluate my Q value function. This is the true Q value function, and this is the Q value function that after K iteration. So I compute their L1 norm with respect to a new measure mu, right? So this mu doesn't have to be the same as this nu. If they are the same, of course, it'll be simpler, but it doesn't have to be the same, right? So this is the thing that we have, and so once you get so what is our output policy, right? So by the way, the output policy is this, right? So once you do K iteration, you got to this Q tilde, right? So you just output the greedy policy based on this Q star. That would be your policy. So the result we got is the following, right? So suppose that I consider again the relu neural nets with depth L, and the width is DJ, right? And then the sparse is S. And then if I choose L to be of log n order, and DJ, of course, it had to be big than dimensional inputs and up to here. So if I properly choose this, and this is the sparsity I choose, then I could show that the neural nets error, the error that we are measuring, the L1 error between these two, our outputs and the optimal one, is controlled by statistical error, right? So this is the optimal rate of convergence for non-parametric function estimation, and is adaptive to unknown degree of smoothness thanks to the ability of neural nets and also to unknown dimension. And this A is the action space, and this C nu is we call compatibility constant, is a concentrability constant, is defined. I'm not talking here, and this is really just algorithmic error. So, and this depending on gamma in the way 1 minus 2. So, so in other words, we basically showed that the deep Q learning converges linearly, up to statistical error. If I just take logarithmic order of K, this would be the dominant term. And this is the optimal rates for, composite like beta Holder smoothness. And the contractibility constant here is defined, but it's just too complicated. I just ignore here. But in particular, these two measures are the same. The sampling distribution and the evaluation distribution are the same. This will be a finite constant. Okay, so as a corollary, so this just repeat the same result using a different statements. So if K is sufficiently large, so in other words, number of iteration is logarithmic order but sufficient large, so statistical error will be like this. This would be the statistical error. And if you're really asking what is the sampling complexity to achieve epsilon accuracy, this would be the sampling complexity. Again, after a while, we probably forget what is our algorithm. So let me just remind you what is our algorithm again. Right. So this is the ideal Bellman operator. If you know everything, you just doing starting from Q0, you keep iterating until you find a fixed point. And in our case, since we do not know, we are not in the ideal world, starting from Q0, I do sample n times, right? And then I got to do deep neural network offline, off policy learning, I got to Q1. And now I again sampling n times using our sampling scheme again. So you learn to Q2 and so on, right? So the above is the actions and the below is the ideal. And we basically shown that the error, right, in approximation from here to here and from here to here is, right, the error basically is of this order. So this is really reflect also in the proof too. So so here is just a quick idea of proof. I know it's pretty late in the afternoon, so you'll not get to any detail, but the idea is this, right? So you do deep neural network fit, right? So this is our Q take star, right? And our iteration is like this, right? So it's based on a new sample, you get a TK, and it's really a composite of each of these, right? And we know each of these statistical learning, one sample size is large enough, would be nearly optimal to, learning this T. So, so therefore, we naturally ask what is the error in this approximation. So this is really talking about the Q function that you learned based on neural network fit, and the true Bellman operator applied this to this Q k minus 1, right? So in other words, you learn this way, and the true one, ideal one you want is this way. What is the error? So this is really the non-parametric regression error, depending on L2 norm that you have. Then you can show that in at least in terms of order, that you are applying this k times, right? So the total error is accumulate, but accumulate can be controlled within an order. We ignore some log n order here by the maximum error, maximum regression error in each offline learning. And now for each of these regression error is very well known in statistics and machine learning, depending on how unknown function can be approximated by your class of function, in this case, neural nets, right? And then plus the complexity of neural nets using delta, right? So this is the delta current numbers, and this is delta. And if I take this delta equal to 1 over n, the current numbers has already been shown for neural nets, shown in the Anthony and Bartlett, so you could just apply there. And then the bias is of this order, and so on. So if you combine this, you get in the result that you want. So how many minutes I have? I think probably not much, right?
You have 10 minutes.
Okay, so there, no, thank you. That would be enough for me. So now the next one, I just generalize the results from single to multiple agents reinforcement learning. And in our case, we only solve zero-sum Stochastic games. So here is just slightly change of the problem. So you starting from, let's say, initial state, right? So agent A, 1 and agent 2 both seen it. So they are simultaneously making decision A0 and B0, right? So in other words, when you taking A0 and B0. So you observe the reward R0 for agent 1. And because it's zero-sum game, so it minus R0 for agent 2. Right? And now the state changed to this new state S1, depending, of course, on S0, A0, and B0, right? And now, again, they are taking an action, and you got rewards. And then if you have zero sum, you get negative reward, and so on. So this is really similar by extending to two zero-sum games. So let me again denote the state space. A and B denote the action space of two players. And this is the reward function. I reward function of player 1 because it's zero-sum game, so I need only 1. And then transition kernel now depending on action of this current state, acting of agent 1, action of agent 2, and this is the unknown Markov transition kernel. And our purpose is to find the optimal policy for player 1 and the optimal policy for player 2 given a state. So in other words, once you see one of those state, what is the action that you are using? Okay, so similarly, we define the Q function, right? The Q function for Stochastic game. So this is the reward, this is the discounting factor, and this is the current state. And now here it's given the action A you take, and that given the action B that you take. So this is the Q. Depending on the policy, agent 1 and agent 2 are using. And of course, the goal is to solve, right? So you want to minimize agent 2 want to minimize the gain by agent 1, and agent 1 want to maximize this, right? So this is the joint policy pi star and sigma star, which is also called Nash equilibrium. And the optimal Q value function is defined by this equilibriums. It could be have multiple equilibriums, but the Q is the optimal one that you are defining. And now you define similarly the Bellman operator, which is really the instantaneous reward you get, right? Plus the next step or the future reward, right? Once they have a reward, so it's discount gamma. And now state, once you get in, starting from here, state now change to S prime, right? So now you have Q value function here, drawing out you have value function here. So you are solving the minimax game in this tabular situation. So that would be the Bellman operator, and the Q star is just a fixed point of this value iteration. So the fitted Q value zero-sum Markov game, in order to be able to prove theorem, we modify and slide the game here, right? So first you have a sampling scheme, tell you how to get in the design point, state and action for agent 1, action for agent 2, right? And then you tell me how many iterations you want, every time how many sample of policy you want to learn, and then just give me initial function Q0. So you sample and data points from the mu that from your design, the distribution from your sampling distribution. Then you get your rewards, and you see how the state transition given the current state, right? And with this, you compute the Y value similar to what we compute before, except now you have to solve minimax game for each given table K, right? And now you do offline learning, right? So this is really your Y value, and this is your X value. So you do neural network learning here, you get to the next Q values. And then of course the output, once you finish the Q value, this is the last step Q value. So your output policy is just minimax game based on this nearly optimal Q value function. So this is the fitted Q value iteration that we have. And then we can obtain similar kind of results as what we have obtained before. So if I consider a relu network, so this is the relu network I'm using, under some suitable assumptions, we basically show that the Q value function that you are care about can be have two type of error, right? So one type of error is statistical error, the same as before, except now B, I have player B, right, times the complexity or the action space of B's. And then this is the optimization error due to the fixed point iteration. Okay, so this is basically the result I have. So let me just conclude and summarize what I have talked so far. So we basically saying that replacing online TD update by offline regression, deep Q learning can find the optimal policy in reinforcement learning, as well as in Nash equilibrium for zero-sum Stochastic games. We showed that the error of deep Q learning converges linearly up to a certain statistical error. So therefore you need just logarithmic order of iteration. And statistical error rely on interplay among function class, deep neural DNA networks, and the sampling distributions. And lastly, we basically say the error, thanks to neural nets that we use, actually adapt to unknown structure of Q star, in which I really mean is intrinsic low dimensionality of Q star, as well as unknown degree of smoothness. And this is all what I want to say. And the paper is in archive.org, just in case that I miss a lot of details that people would like to ask for additional details. Thank you.
Thank you, Professor Fan. And yeah, I think I'd like to start with a question and then see, if we have the audience to ask questions. So my question is that for your work, it really seems to me that it integrates many aspects, like from statistics, from functional approximations, from reinforcement learning, and also the structure of deep neural network. So I have two questions on the elements in it. One is that in terms of the offline regression, do you think there is a room for improvement for that step? And second, that in terms of function class, right? So if the function class deviates, so what do you think that this method will be readily extendable to a broader class?
Yeah, so yeah, I mean, both are very, very good questions. Yeah, I think you are right. Of course, at the higher level, right? So it's really just like offline learning, of policy learning, trying to estimate the Bellman operator, and then you apply this. So when you actually let's say when you're actually trying to prove it, all these kind of things, of course, there's a lot of details. But in terms of idea, yeah, there are, in terms of idea, I think you are right. There's a lot of also work here in terms of engineering. Right? So what kind of network actually we are using here, and so on. So, and then also like if the true function is not in this class. And so there's a lot of like approximation error that will incur in or this kind of learning. But at higher level, your summary is quite correct. We basically, learning by through statistical estimation. Now, in terms of you are asking, so where should I put in the off policy learning? Like where should I put in the data? So currently we just put a new, basically saying any distribution, but of course the optimality, optimal design is not really just putting any distribution. So there's a lot of issues on where to do active sampling too, right? So within neural nets, it's not clear, right? There's also, just like most of things, they also have bias and the variance trade-off there. So there's a lot of study should be made. We just make a part of study just to understand what is this deep neural network. But all the questions are well taken. Yeah.
Yeah. Thank you.
Yeah, so if I can expand on part of Zayu's question, or maybe a slightly different version of the question. So your analysis focused on these sparse relu networks, right? So I'm wondering, is the analysis generalizable to other networks with the same sort of statistical guarantees, or other learning methods with the same sort of guarantees, or is there something really special about the relu networks for your analysis?
Again, this is a very good question. So I think the analysis it should be generalizable, because I was looking even in earlier paper, let's say by like a Susan Murphy on those errors and so on. So I think it should be generalizable. In particular, you actually point out a very good, good points like sparse neural nets. So when I see the paper, the discussion of the paper by Schmidt-Heber, there's a lot of criticism on the sparsity, because this is not really the neural nets people use. So I actually impose the same question to my student. I say, hey, take a quick look to see if dense neural net will work. Right. So I guess I think we are taking a quick look, and I believe like let's say this one, let's say dense neural net with fixed width and let's say deep net. I'm pretty sure this one will work just by following very much similar similar duration. And the main reason is this, right? So if I have let's say n width like this, the depth is n and fixed width, so then the total number of parameter would be a constant square times n. I think that the whole thing will work. I'm not sure whether this would be like for issue like this, whether it would be too many neurons for too many parameters for study or not. But the question you're asking is quite relevant. But in general, I believe it's applied broader than just sparse relu neural nets.
Thanks.
Other questions from audience? Professor Fan, thank you so much for your time and coming on this virtual visit and giving us this really inspiring talk. And we hope that we'll be able to invite you in person in future semesters when everything is more clear.
Thank you. And I wish you will have an opportunity to talk with my colleagues there in Ori. So thank you very much. And, have a good day.
Yeah, thank you so much. Yeah.
Bye-bye.
Yeah.
Thank you.